Okay, hello everybody. Welcome to the lecture by Vladimiro Paschali from the University of Rome, who is invited for today's mutualized shared. No, I think okay. Thank you. Can you double check if you
Sasa?
Yeah. Okay.
Can
Great.
you hear me?
So Vladimiro will talk about high-speed networking, and in particular in cloudified system where the networks are virtualized. We have seen that when you do packet processing by means of software, you have more flexibility, but you will be slower than the real hardware. So what Vladimiro will show us is a panoramic view of high-speed virtualized systems, and which is part of the class of the lecture. And then he will show us the results of his research.
Thank you for the kind introduction, and thank you all for being here, even if some of you are forced to be here by the professor. I'd like to speak to you about high-speed packet processing, and especially the network kernel stack bottlenecks, and how to skip them to achieve line rate packet processing. So a little bit of introduction about networking. At the dawn of networking, there were few hosts, just a few hosts, few servers, and some routers to switch packets around to serve the communication. Unfortunately, sooner things became more complex as network grew and also requirements grew. The first one was definitely security. So it forced the introduction of firewalls to protect servers from unwanted traffic. These were hardware devices that were expensive, inflexible, but they were very fast doing their work. They could only do one thing since they were hardware, and that thing they did it well. Another requirements that became important was to detect performance issues and hopefully mitigating them, which required the introduction of another different hardware, which is a monitor that just simply checks the flows of the packets coming in and out, and seeing the performance where they could be lose performance. Sooner, because of the number of users accessing the servers were increased rapidly, it was required to have multiple servers and a load balancer between them to spread the load across multiple servers. Again, another hardware device that worked very, very well. Unfortunately, all these devices were very expensive, very inflexible, and they also stacked as physical hardware, and they were also expensive to store because they required additional storage inside the data center. So they thought, why don't combine all this hardware inside a commodity server, a commodity machine like the one used from the servers, and have it all in software. And this is the start of virtualization, where all the previous functions, networking functions, were implemented inside virtual machine, inside the same server as the one used to serve the application, which reduced by much the cost of all this equipment, and also helped with flexibility, since it was all software and could be updated and managed way easier than hardware. Unfortunately, virtualization has its problems. Mainly, it's slower performance than hardware. To increase performance while preserving the low cost and flexibility that virtualization gives, they understood that the main problem of the main slowdown of this architecture was the Linux networking stack. And so they find some ways either to skip it altogether or to mitigate or to limit the use of this stack through either eBPF, the little b, or DPDK, which we'll explain in a moment. And these two techniques preserve the flexibility of the software while achieving much higher throughputs than virtualization. But why do we need faster way to process speed? Simply because Ethernet speed are going faster and faster. Right now we are in the 400 gigabits range, and server needs to keep up with that traffic. Unfortunately, processor speeds and performances are not going up as fast as the networking speed. So we need to find a new way to process packets and to serve all this application. But why we don't simply throw more cores at the problem? We have my laptop has 10 cores, servers have 6,400 cores. We could simply spread the load across these multiple cores. After all, the new NICs implement this feature through the use of multiple receive queues where packets are put and usually linked one-to-one to another core. So through the use of RSS, or receive side scaling, which is a technology that hashes the IPs and ports of the packets. This is called the four-tuple. And through the result of this hashing, it distributes the packets on the various different cores. This increases core utilization and throughput because you are spreading the load across multiple cores, but also cache locality because usually the same core is serving the same kind of packets and the same kind of application, which helps with cache because most likely the stuff needed for the application is already inside the cache. Unfortunately, RSS is not perfect. It cannot balance core load evenly or spread the packets evenly, even because it could happen that the traffic coming in is not even. Some cores may be allocated with heavier flows called elephant flows, which will take 100% of the CPU from said core, while others will be allocated with mice flows that are lighter flows, easier to handle, and will remain mostly idle, while the other cores are completely full and dropping packets, and so not performing as well. This reduces the overall efficiency and scalability of RSS. An example could be an IP tables firewall that simply drops every packet that it receives. This can achieve around 5 million of packets per second for a single core. If, and I say if, the throughput were to scale linearly with the number of cores, we could need around 30 different cores to serve 100 gigabits application. So it's not really feasible to devolve all these cores just to a simple application. We need to find the cause of the bottleneck and to solve it.
Can I ask a question?
Sure.
So the question is, if you go back to the previous slide, is that if you allocate 30 cores just for the networking, you do not have any additional core for your VMs?
Also that, yeah.
So the reason why this does not scale well is also because resources are constrained. What you do for networking, you cannot do for compute and vice versa.
Yeah, although maybe half the machine is still is only doing networking, it's still too much to have half a machine doing just networking and just a simple application. The more complex application, of course, tend to use cores and power more heavily. So what are the main causes of overhead, specifically inside the Linux networking stack? First of all, it's complex. It uses it has a lot of functionality, a lot of layers, and every layers add a functionality and overhead. You can pick and choose what functionality you want. You are stuck with all of it. You simply need to use them, even if they are not necessary for your application, and they will induce a lot of overhead. A solution could be to simply re-implement just what you need, maybe in user space, maybe in kernel space. Another problem is the socket buffer allocation. This part here, the big one, which is the copying of the data structure of the packet from kernel space and the user application. There are some fixes, mainly using either DPDK or eBPF, which allow to mitigate this problem or skip or eliminate altogether this copying of the packet. And the last one, which is a little more maybe more sneaky, is the PCI transaction between the NIC and the CPU here, where every packet requires a new PCI transaction to be put inside the kernel. And unfortunately, there's not much we can do because we still need one PCI transaction, but we could batch multiple packets inside that same PCI transaction, since most of it is used by metadata that could be shared among the various transactions. Let's move a bit more in depth with why we need this copying between the kernel and application and what is actually happening. So the packet is stored inside a file descriptor at the beginning that needs to be copied inside this socket buffer, which is a struct that contains all the necessary components for the user space application to use that said packet for its job. But why do we need the copy? First of all, we need to free the descriptor as fast as possible because we only have a limited number of descriptors, and if we free them, the sooner we free them, the sooner we can receive more packets. The second problem is that if we don't copy the packet, we could read either from wrong packet, corrupted memory, or something like that in our application. And the last one is maybe more philosophical than others, but for security reasons, we need to keep the memory of the kernel separate from the memory of the application. Especially, we don't want the application to mess with the kernel memory. They must be completely different and isolated. The PCI transaction, which I was talking about earlier, it's slow, and it is generated at least one for every received packet. Most of it is consumed by metadata, which could be shared, as I said, among multiple packets, reducing the number of transactions and therefore the increase in throughput. Also, we have a problem with this transaction and the type of workload we are using with networking. Usually, networking workloads are sequential. Packets are coming one after the other, whereas the PCI transaction is supposed to be working in parallel as much as possible. And that's an ulterior problem that we have to solve. So we said that the kernel, the Linux networking stack is complex and expensive to execute. It has many layers and introduces much overhead. Why don't we just keep it? Intel DPDK does this. It writes the packets data directly into user memory. And then in the user space application, you can decide whatever to do, whatever you like with your application. DPDK is fast and can reach up to 30 million of packets per second with one single core, depending, of course, on the application and on your machine. But it's one of the fastest ways to skip, to accelerate packet processing. Unfortunately, it's not so easy as saying just keep the kernel. You need, first of all, a new driver. Your NIC has to be bound to a user space driver, usually VFIO PCI, which gives the application full control of the NIC, which means that you lose completely control of the NIC. You can do EP-link, TCP dump, ipconfig, all the configuration stuff that you usually do in your computer to manage your network, your networking stuff. Instead of relying on interrupts like everyone else does, DPDK uses busy polling, which means that it continuously checks for new packets that are inside the NIC or inside this, the user space for the packets, which means that your core will be always full, always busy at 100%. To store packets inside the user space application, DPDK uses huge pages, which are bigger memory pages, continuous memory pages, usually from 2 mega to 1 giga, instead of the classical 4 kilobytes memory pages that are used by Linux. So with all this feature, the FIO PCI and used pages, the NIC can directly transfer packets to user space, eliminating copies and the need for the Linux networking stack. So we have some pros and some cons of DPDKs. The cons are mainly high performance, thanks to this zero copy we don't need to wait for the copy. Usually copy, data movement, and data management are all a big problem, even from different application, different functionalities. Low latency, thanks to this busy polling, we don't need to wait for the interrupt to be raised and then to be cached by someone else. We can just check if there is the packet, okay, process it, otherwise no. Excellent multi-core performance, since every core can decide where to take the packets, where they are distributed inside these huge memory pages, and ease of development and developing, mainly because it's a user space application. User space debuggers, user space profilers are much better developed than the kernel ones, and you won't crash the machine if you mess up in your user space application. Unfortunately, there are many cons, most of which are from the usability point, especially the full core control, which requires every DPDK application. If you have a DPDK application with 10 cores allocated, you will lose control of all those 10 cores. No matter if you have traffic, you don't have traffic, you lost it, which means, first of all, energy efficiency. You lose energy efficiency because your CPU won't ever go idle. But also you can do other processes on the same machine, or at least on the same cores. If you have the whole machine dedicated to DPDK, you have lost your machine. You can do anything else but the DPDK application. Similar thing for the NIC. As soon as you bind it to UEFI PCI, the new driver, you lose control over it. Control is taken, of course, by the application, but you can do anything else on that NIC. And most importantly, you lose any Linux networking feature that were already implemented. They need to be re-implemented again inside your application. For example, ping won't work unless you're implemented in your user space application. But it's fast. That's the main part. Another way to reduce data movement is to move part of your application processing inside the kernel itself. After all, the kernel is open source. It can be modified, and either through the editing of the code of the kernel itself, or by adding a custom kernel module, which can be attached to the kernel and does some processing inside the kernel itself. This decreases the movement and the copy if your application supports it. Unfortunately, if you manage to create a new kernel, a new feature inside the kernel, you have to maintain it, which means that every time the kernel gets updated, you need to update it as well. Otherwise, if your feature is so good, you could ask the maintainer to put your feature inside the mainline kernel. This is, it usually won't happen. Let's be realistic. Maintainers are very strict on what goes in the kernel and what goes in the mainline. Another big problem about kernel programming is that it's hard. Development, debugging, and profiling will lead to system crashes, and the documentation, the tools, and the profilers are usually not so well developed as well as the user space ones. Fortunately, eBPF comes to the rescue, at least for the crashing part of the kernel. eBPF is a virtual machine that runs inside the kernel and thus allows for safe execution of sandbox programs inside the kernel. This is used to safely expand the kernel functionalities without changing the kernel code, loading new custom kernel, or having to reboot the system for new features. eBPF provides a wide range of programmability. Usually is used for kernel tracing, system observability, so understanding what's happening inside your system, CPU scheduling, and system control, and what we are interested in this presentation, packet processing and networking. These are some of the observability tools that were developed using eBPF. As you can see, they go from device driver to application. Probably there is an eBPF program that you can use, an eBPF tool that you can use to fix your problem already. An important thing is that Linux eBPF is supported on Linux, Android by default. Windows, you have to do some kind of trickery, but most importantly, you can run Tetris on using eBPF. What are eBPF programs? So they consist of two components: a user space component and a kernel space component. The first one, the user space, is responsible for loading and attaching the eBPF, the kernel part of the program. This can be written in many programming languages, from C to Python, going to Rust and Go, for example. For the kernel space, and it's used for setting up the kernel space program and communication between kernel space and user space. The kernel space program instead can be written either in C or Rust, and this was actually it's executed inside your kernel and performs the actual processing that you're programming it for. So, as we said, the eBPF program are written in restricted C or Rust. There are many things you can do inside an eBPF program. For example, no unbounded loops, no weirder pointer arithmetic, and no unsafe memory access. And
yes, sorry.
No.
eBPF, you want to write a simple kernel driver, or is it not the same?
So you don't need a BPF to write to modify or to write a kernel driver. Yes, the problem with the BPF code is that you have to find somewhere to attach it. It's need to be put in a specific place inside the kernel, which can be not what you're looking for, probably. Otherwise, if you're looking for packet processing or even system trace, most of the stuff, you can use a BPF. Anyways, and another important thing you can do is dynamic allocation of memory. You can do malloc, calloc, or whatever. Once you write a program, you can compile it using Clang or using the Clang compiler into the eBPF bytecode. Before being executed and attached, the eBPF bytecode gets passed to the verifier. The verifier is a very complex static analysis tool, which, after all, it ensures that the program is safe. It does a lot of checks, most of which are memory safety, meaning that it's checked if you are reading or writing from the memory region you are supposed to. For example, inside a packet, it checks that you are not reading outside the boundaries of a packet. That there are no infinite loops, meaning that the eBPF program will eventually terminate. It prevents invalid pointer arithmetics, but most importantly, that you will not crash your system.
Question. So for those with a bit of knowledge of language theory, this means that it's not Turing complete, right?
I'm not sure about it. There were some articles saying that it was, but I'm not so deep in that, that part of eBPF, especially because I'm scared of the verifier and how complex it is. eBPF maps, so eBPF programs are stateless, meaning that the kernel part of the program gets executed every time an event passes through the eBPF program, or is executed always the same. To have some more complex programs, you need to maintain state across multiple execution of this program. This is done through maps, which are a key value store like array, hash, or ring buffer that can be accessed both from the kernel space and from the user space by using some helpers, which are simply functions that look up or update the map itself. Unfortunately, maps are slow and they are necessary to make good eBPF application, but should be used as less as possible. Especially the more complex one, they incur in very high overhead. So eBPF programs are event-driven and are run every time the kernel or an application passes through a certain hook where that eBPF program is attached. There are some predefined hooks, like system calls. You can attach program to every system calls. Most kernel functions can be modified and checked through the use of functions that get attached before or after the execution of the function. Trace point, and what we're interested in, network events. This is the networking stack, and as we can see, these are the places that an eBPF programs can be attached. An eBPF program can be attached. The lower, the faster. The higher, the greater information about the packet you have, because it's already being unpacked and managed by the Linux networking stack. For our presentation, we will be talking about XDP, which is the lowest level of the Linux networking stack. It's a high-speed hook executed at the earliest point in the stack. Most importantly, it's done before the socket buffer allocation, and therefore the expensive data copying and data management of the socket buffer. XDP programs can inspect and modify packets, and after the execution of a program, it returns to the driver a verdict on what should happen to that packet. These are the return codes that are the verdicts of XDP. We have redirect, where we are sending the packets to a different interface. Pass, which we are sending it through the network stack as if nothing happened, or with the modification that we did to the packet. Drop, which simply eliminates the packets. And TX, which transmits it back to through the same interface. Here we also see IFXDP, which is the eBPF way of doing kernel bypass, similarly to what DPDK does, but with the benefits of eBPF, which we'll talk about later. So this is a simple eBPF program, the simplest you can find, you can create, and also the most dangerous, because it drops every single program. If you are connected through SSH to a machine and you attach it to the wrong interface, to the interface you are using for SSH, you will lose access to that machine, and you will need to reboot it or go with a physical access. But here we have the hook point, which in this case is XDP, the lowest one. The packet context, which contains all the pointer, it's a struct containing all the pointers that we are interested in the packet. The verdict, which in this case will drop everything. And the license, which is required by the verifier, otherwise the verifier won't let your program pass. A bit more complex application is a NAT, network address translators, that translate the EPs coming from the packets coming in to some set of EPs that are predefined. In this case, we want to access the packet, so we actually need data and data end, which are the start and the end of the packet. This pointer gets passed to this getEP function, where we unpack the data inside the Ethernet struct. As soon as we try to read any pointer, we need to check that we are inside the boundaries of that pointer, of the packets itself, so that we are before data end. Otherwise, the verifier won't let it pass. Through the Ethernet header, we access the protocol, and same thing with the IP header, accessing the IP address. Also, while doing this check for the IP, we need to check that we are inside the boundaries. A bit repetitive, but necessary. Then we get the IP, and we look up inside the map what is the correlation between the IP we got from the packet, the received packet, to the one that we want to put inside the packet itself. So we put the IP inside the map, we look up it, and we get the new IP. We do some little bit of checks that we actually got the IP, otherwise the verifier will block it. And we update the IP address. The function is mostly similar to that one. at the end, the return code, which is XDPTX, retransmitting the packet with the new IP address through the same interface. So which are the pros and cons of eBPF, particularly about XDP? It already runs inside your kernel, especially if you're using Linux. There is no need for kernel module, kernel patches, or anything else. It just runs, supposedly. Safety, thanks to the verifier, we can guarantee that the program we are attaching won't crash the server or the machine we are working on. And the flexibility mainly because there is no busy polling. So if there is no traffic, the core is actually idle, and the NIC can be used for other features because we are not binding it to a different driver. And the dynamic loading and unloading of programs, because it's simply you kill the program and you can keep running as if you never attached it. Unfortunately, it has a much lower performance than DPDK, reaching around 15 packets for the million packets per second with one core for the same applications. This is because everything is run per packet. So every time a packet arrives, a new PCI transaction is done, a new call is done, and access of the map. This is done everything with for each packet. There are some other verifier limitation. This is both a con than a pro, because as soon as you start doing some more complex stuff, you will encounter problems with the verifier saying that your program is not safe and you need to fix it. The development complexity, unfortunately, is still a problem because you are programming kernel application. Now, likely the BPF community has a lot of support and somewhat good documentation, but the profiling part of the kernel application of eBPF is still hard and expensive to use. Expensive as in overhead, not money. How is? Sorry? So it's supposed to be good. There are some, the BPF program can be run separately on different cores, and there are some maps that are done especially for that, meaning that they are replicated among different cores, so there are no problem with locks and unstable data. That's the main part, and also since it is integrated inside the kernel and is after the receive side scaling, it automatically works on multiple cores as long as you set up RSS correctly. Hope it helps. Here are some of the XDP limitation, most of which are due to the per packet execution model, meaning that for one packet, we have one PCI transaction. For each packet, we have the function call that is executed to call the XDP program that has a cost, and the map accesses which are executed again for each packet. Due to the limited data we are working on, because it's simply just a packet, there is also limited opportunities to use SIMD. SIMD are single instruction multiple data, are a special instruction that do the same instruction on a lot of data together. This is usually multiplication, sums, and things like that. They go really fast, but you need to have enough data to support the use of this function, because it has a cost, as always, as everything. So with the batch execution model, which is usually done with DPDK, we can share PCI transactions across multiple packets, since they are almost all metadata and similar with regarding the same packet. the function to call the XDP programs as well can be shared with multiple packets. Map access the same, and better sim utilization simply because we have more data to use and to leverage these instructions. This is my research. Let's stop. Yes, it's not going.
Okay, so
I checked.
yes.
I think it's the presentation.
Yeah, because outside, I think everything is good.
Okay. I got kicked out because of internet.
Okay.
Eduroam doesn't
Yes. Okay.
doesn't help. Mi puoi ridare?
Allora,
Sì.
3491
3491 0554. Ok. Vai.
74
674
39
839. Okay, I should be back. Sorry for the inconvenience.
Yeah. Yes.
Okay, perfect. So my research is mostly focused about the eBPF, as you might have guessed, and this batching part of XDP, making it possible to reach the same performance as DPDK. This is done through hardware-assisted batching, which required a smart NIC to put multiple packets inside the same Linux memory page. And afterward, this big packet get sent to the kernel space and it invokes a single XDP call for for multiple packets all at once. Inside the XDP program, you can select the outcome of each individual packet, and then a splitter function inside the kernel itself decides what to do with each singular packets. But what are smart NICs? They are simply NICs with some programmable compute capabilities, allowing it to offload network tasks directly to the NIC hardware and logic. So we are going back to hardware. Kind of, it's not really the same hardware that we talked before. It's programmable hardware, but it has a cost. Mainly, it's hard to program. It requires Verilog. It's a difficult programming language, just at that, and it's expensive to buy and operate. I think. So these are some of the XDP applications that we have used for our evaluation of X2DP. The first three are a simple one instruction program, simply returning what the action is. So drop drops, the X retransmits, passes through the kernel. These are two real complex applications. The first one is the NAT, like the one we saw before. And after the CMS is a count me sketch, which is a monitoring application that is used to check information of each flows passing inside an application, usually hashing the packet and updating a data structure. These are some of the results. As you can see, the biggest jump in performance happens between batch size of 1, which is regular XDP, and batch size of 2, which is the smallest implementation of our framework. For example, in the NAT, we can see that here as a batch size of 1, we are limited by the instruction itself, DTX, which is 5 and 5 millions of packets per second, more or less. But as soon as we remove that bottleneck, we get to another bottleneck, which is the application itself, which is slow because it has some checks to do, and we are bottlenecked by by the application. For the pass program, we can't get much improvement simply because we are passing the packet to the Linux networking stack, which, as we said, is slow. It does almost 5 million of packets per second, and that's what we can get for it. The other application, like the company sketch, can get much higher, but again, they are usually limited by the application itself, unless unlike the drop, which simply does nothing, it drops and can reach up to 80 million packets per second. This is due to lower processing overhead, better cache and TLB utilization, and more efficient CPU usage. Thanks to the batching approach, we can also share the price of the PCI transaction across multiple packets. For the receival of the packets, we have only one PCI transaction, so we can get 1 divided by the number of packets inside the batch and share it this way, which helps us a lot. Unfortunately, for retransmission, it's not so simple because the items are the write PCI operation and is 1 for each 64 bytes of data. So batching helps mainly because of this extra write to the DLC cache, which can be spread across the packets. Otherwise, the packet data, that's it. If you have multiple packets, for 64 bytes packets, you have to pay for ETOM transactions. So that's why the decrease in the blue one is not as good as the red one. As we told, we process the packets all together inside the XDP, having a kind of seamless XDP integration. This is a regular XDP program. It's not the NAT we saw before, but it's the count me sketch, where we look up the map. We handle the packet, meaning that we put the 2 EPs, the 2 port, and the protocol inside this data structure packet. Then we hash it all together, and then we update the count min map with the result of the hash, making the application understand which flows are coming inside the application. This is what we do for the batched version. Same stuff at the beginning. This data meta is a metadata we use simply to check if there are how many packets are in the batch. So we have a for loop for each packet. If said packet is inside the batch, we do the same thing as before, and then we return the various action derived from this function here.
Question. Is that check enforced by the verifier, or you used it?
So the verifier simply wants that we return a valid number. I think it's 32-bit. We use this weird bit mask way of returning the code simply because it was easier to unpack it afterwards in the kernel. You could return even in different ways. This was easier because we had also less problems with the verifier. Yes, simply because this is just a number at the end. But for the verifier, is a number. But now we have the context of 4 packets altogether. So instead of doing the for loop like in the naively batched version, we call it like that, we do some further optimization, which is loop unrolling and code reordering. Through doing this, all these functions together, the same function together for different packets, increases the instructions per clock done by the processor, and therefore also the speed of the whole application, and so the throughput. These are some of the results of the optimization. So here we have the single packet version, the naively batched. The orange one is the loop unrolling and code reordering. And where applicable, we also implemented SIMD instructions, which gained us 2 more millions of packets per second. It's not much, but is, let's say, research interesting in the research performance for the performance. So at the end, chord reordering and loop unrolling gained us from 10 to 40% gain in the application. Here I have a little video of the application running. This is a demo we presented. So we have on the left, this is the code for the count miss catch. This is the naively batched version, the one with the for loop and the returns code done this way. And here this is in purple, is the throughput varying among the various batch sizes. When we go from 2 to 3, it's a batch size from 2 to 3, 3 to 4, and so on. We can see that the greatest improvement is here. It's actually here, from no batching down here to here. Now we have the optimized version, which is as we told before, the compressing of the operation together, the loop unrolling and the reordering of the operation all together. And we can see that without batching, we get 12, 20 with a batch size of 2, 3, 4, and this is with the reordering of the packets of the instructions. This is. It seems like a still image, but it's actually a video. Oh. Optimization. Here we have the same thing, but with the NAT. So the update of the IP address and the retrieval and update of the IP address. And also here we can see that the biggest gain comes from 2 to 3. The loop unrolling and code reordering part, which gains us 5 millions of packets again. I think that's it. So, conclusions. Why not stay with hardware? After all, it has great performances. Unfortunately, it's not flexible. It's complex to configure, update, and develop. Why not use the Linux networking stack? As we saw, there are a lot of bottlenecks. It's feature-rich and complete, but it's too slow for high-speed packet processing. DPDK is good if you want to go fast. Unfortunately, it has its drawbacks, especially the ones from the lack of control over the core and over the network interface cast. eBPF is a good compromise among the two that runs safely in the kernel and has a good balance between speed, programmability, and system integration. And then we have my research project, which is X2DP, that brings the batching benefits to XDP, closing the performance gap with DPDK. Thank you very much.
Okay, so if you have questions, I would give priority to the students and then to the researchers in the room.
Bonjour, je m'excuse, hein, je vais parler en français.
Eh.
Donc, je n'ai rien compris de l'italien, un peu compris l'anglais. J'espère que en fait, je m'excuse, peut-être ce sont des questions bêtes, mais l'essentiel pour moi, c'est de vraiment fixer ce que vous avez essayé de dire.
I will translate later. Go to the question. Je vais traduire après, vous allez la question.
Ok, d'accord. Alors, j'aimerais savoir, j'ai pas vu là où peut-être en essayant de faire vos essais, j'aimerais savoir d'abord dans quel cadre, de quel type de CPU, disons, la puissance du CPU que vous avez utilisé. Mais moi, le plus important, soit du côté DPK, DPK, DPDK ou soit les eBPF. J'aimerais juste savoir comment réagissez ou quel était le comportement de du CPU. Parce que j'ai l'impression que vous avez trop parlé bande passante, il a trop parlé tout ça, la carte réseau et tout, mais j'aimerais savoir quel était le comportement du CPU.
So what is the role of the CPU in that? Is the frequency impacting the processing compute, the power of the application? Is this a relevant metric or not?
We fixed for our test, we fixed the frequency of the CPU to 3 gigahertz, I guess, or something like that, without allowing for two booster. But for the case of eBPF, the frequency could be higher or lower depending of the actual use case and the actual load in the CPU. Whereas for DPDK, if it's fixed, it's fixed. Otherwise, it's always at the top, always the fastest.
And is it always the same for all your experiments?
Yeah, we fix it to the same CPU and the same CPU frequency to, if I don't remember wrong, it's 3.1 gigahertz.
Intel
CPU. Yeah, the server grade Xeon something.
Tous des Xeon Intel 3 GHz fixés par DPDK et variables pour eBPF. So I assume that the bottleneck, so it does not depend on the frequency, it's
something else, yeah.
Et la fréquence n'est pas importante parce qu'en fait, les goulots d'étranglement étaient ailleurs. Donc,
il y avait ça, disons, en utilisant bien sûr des ressources de il n'y avait pas une variance du côté de mon CPU.
Non, parce que l'importance, c'est le passage entre les modes
du côté de la carte, en fait.
Voilà, c'est non seulement la carte, c'est aussi les noyaux.
Oui.
Et can you go back to the slide maybe 20ish where you show the AF XCDP for the... je vais vous montrer donc ça. En fait, si vous avez... vous vous rappelez ce qu'on a fait au niveau des systèmes de virtualisation, les systèmes d'exploitation host et guest. Là, vous avez un host qui a un stack TCP/IP. Et là, dans l'application, vous avez un autre guest qui a un autre stack TCP/IP. Donc, il y a de la redondance. Donc, ça veut dire que si votre application doit passer d'abord par le network stack et après pour un autre network stack, ça va être beaucoup plus important que si vous utilisez des CPU à 5 GHz de fréquence.
D'accord. Et j'aimerais savoir une deuxième question. Vraiment, personnellement, je tiens à vous féliciter et à vous remercier parce que là, vraiment, il a parlé de beaucoup de choses qu'on ne connaissait pas. Moi, c'est la partie eBPF. J'aimerais savoir, est-ce que en utilisant ce type, avec le codage dont il a parlé, est-ce qu'on est obligé en faisant ça de rajouter de couches supplémentaires de sécurité? J'aimerais savoir.
Okay. So first of all, congratulations for your research and for your context. And second is for eBPF, do you need to add a security layer or is the security layer already verified by the verifier?
The security, what do you mean by the security layer? The fact that it won't crash the server.
Vous voulez dire quoi avec niveau...
Parce que j'utilise du code, donc
c'est du code, donc...
Quand il y a du code, je vais être sûr que mon code est bien
c'est nous qu'on doit être sûr que les codes marchent ou c'est... OK.
Maybe in English.
Yeah. So, yeah, in the sense that is it us who need to to make sure that the code is safe or is there a automatic verification step? So is it an additional layer or it's just integrated in how eBPF works?
We need to make sure that we do the checks, otherwise the verifier won't let it use. So
c'est à nous qu'on rajoute les checks. C'est à nous qu'on contrôle que notre code est safe.
Ah, d'accord. Ouais, sinon, pour le reste, gracias.
D'autres questions? C'est à vous?
Thank you. Regarding the DPDK accounts,
yeah,
you talk about drawback linked to the to the pooling. I don't catch why you go fully in the pooling since we can be notified when we receive the data.
We don't want to get notified because it's faster simply to check every time that if there is a packet or not. Otherwise, we would need to implement inside this new driver a way to have interrupts and to wake up the application when it receives packets. And it most likely we lose a lot of performance. So the busy polling is part, but an important part of what is making the application fast, the DPDK fast.
I will make an example in French. L'exemple que vous avez, c'est vous êtes là-bas et il y a quelqu'un qui toque à la porte ici, toquez, vous descendez là-bas, vous allez ouvrir la porte et la personne rentre et vous revenez là-bas. S'il y a quelqu'un d'autre qui revient, vous devez refaire le même passage ici et après vous revenez là-bas. C'est beaucoup plus simple de regarder comme ça. Il y a quelqu'un? Non. Il y a quelqu'un? Non. À condition que vous consommez 100% de votre temps en regardant s'il y a quelqu'un ou pas. Mais dans des situations où vous avez toujours des gens qui arrivent, s'il y a quelqu'un à la porte qui ouvre, qui regarde si ouvrir ou pas, c'est beaucoup plus efficace que de se repositionner à sa place, revenir ici au moment où il y a quelqu'un qui a toqué. Donc, ça, c'est l'équivalence entre interrupt processing. On va faire des labs, des TP sur event-based programming quand on va parler de function as a service et de allouer de manière continue quelqu'un à 100% à faire juste l'activité de contrôler s'il y a quelqu'un ou pas.
So my question is more about the eBPF community. What's today in the industry? What type of work do they produce? Are they working with the manufacturer, or what type of work does the eBPF community produce today?
So the eBPF is linked to a foundation which is which allows for free software. Every eBPF program has to be from the GPL license, and so I don't remember very well which are the requirements of this GPL license, but it's a bit stringent. There are some companies that are built on top of eBPF that do some, usually is used for Kubernetes, checking of application among Kubernetes clusters or Docker images, that kind of stuff. There are some companies either that will sell you the programs doing that, the dashboards, or they are used by the programs by the companies to check if they are doing their work right or if they can gain some performance and reduce their cost on the servers.
Okay, and one last question. So that means at one point, if the work on virtualization go further, it will present a risk to the nowadays manufacturers of physical components.
I don't know. I think they will still always have a job, and there shouldn't be any problem for the manufacturers because there is always need for hardware. There are the virtualization techniques helps, but also hardware it's important and will.
Yeah, if I may add to the reply, is that the hardware are becoming more and more similar, interchangeable. So maybe manufacturers would have other ways to differentiate one another, but basically today's hyperscaler data centers, they want servers that all look alike. They don't want a server that is more special than other. They want all the same Intel CPUs or AMD CPUs, and then they specialize on some features like I have 2 NICs or I have 3 NICs, I have more space for PCI, I have more space for add-ons. So hardware will become more and more, it's like mobile phones. In the end, all mobile phones look all the same. It's not, if I look from the distance, my mobile phone is exactly the same as yours and you don't even know what is my brand. because it's an unknown brand. But in the end, the design is what counts. D'autres questions? Can we have the slides?
Yeah, of course. There you go.
Okay, so for the researchers, is there any question?
Oh, pela.
Sorry. I was wondering, have you tried the batching with more than 4 packets, and how does it scale? Given that DPDK has a very large pages, which is megabytes, which means like hundreds of packets probably, and if it's gigabytes, it's even more. So
So we were limited to 4 packets because of
the return value. Don't tell me.
also mainly because of the return value, since it was the biggest jump was from no batching to 2. But also there were some implementation in the FPGA which caused problem going higher. But mainly we didn't even try to fix them because of the
It's
diminishing
already
returns.
quite a good performance increase. So
Yeah.
Congratulations.
Thank you.
Okay, let's thank again the speaker.
Thank you.
Alors,